So thank you very much for the opportunity to give this talk. So I present about the entropic cost and optimization for Brownian thermal shortcuts. And you are seeing the wrong screen. Sorry. I think I need to share again the screen. Where is it? Okay, now I can. Okay, the screen is wrong, but it's okay then. So I present about the entropic cost and optimization for Brownian thermal shortcuts, and this work has been developed on the University of Strasbourg and on the group of Sihak Gende. So the context here is that it's a confined Brownian motion, and in which you have the overdamp dynamics. In your system, we implement a stochastic force that comes from a radiation pressure. The idea that the amplitude of this stochastic force changes the temperature of the thermal bath in a way that we have equilibrium conditions when the instantaneous variance from this Brownian particle it's equal to the instantaneous temperature of the bath. So every time that you measure a difference between instantaneous variance and temperature of the bath that is given by this amplitude of this stochastic force, we are in a non-equilibrium condition. And in order to measure this instantaneous variance, we repeat several times a protocol in which we control the amplitude of this stochastic force. And by changing this amplitude, we change instantaneously the temperature of the bath. And by doing this, we produce a non-equilibrium state in which we have this idea that our system will evolve from one initial equilibrium state to the other. And at each time instant, we are able to measure a probability distribution. And this probability distribution is what we address as the macro state of the system, while the stochastic position for a given time is given the micro state of the system. So subject to this quench in temperature, so we are able to define a relaxation process, and this relaxation process giving an exponential and asymptotic evolution of the system towards this new equilibrium position. And for us on this system, there is only one single relaxation time that's given by the position correlation time. And this time defines what we call natural relaxation. And for this problem of natural relaxation, the question is raised, so how we can accelerate this transition?
Luís, very, very quickly, we're seeing 3 slides at once rather than just 1 slide at once.
Yes, sorry, I tried to change here, but I was not able. So the actual slide is the one on the left that I'm presenting. Okay, sorry if it's a bit small, but it's okay then. So then I'm focused on this slide on the left. So the idea to connect 2 states at a finite time, and in which this finite time, this delta t, it is smaller than the correlation time in position. So this kind of method of accelerating those transitions was already implemented on the literature on those kind of methods called EASY, that is engineer swift equilibration, in which those kind of methods rely in the idea to impose equilibrium conditions in the beginning and in the end of a protocol. And here we adopted this kind of approach for a temperature change in which we assume both initial equilibrium conditions in the beginning and the end of the protocol. And then we are able to accelerate thermal protocols. For us, temperature here, it's a time-dependent control parameter. And by doing this technique of doing an overshoot, by overshooting the temperature, we are able to both increase or decrease the temperature of the final equilibrium state. And by this idea of accelerating, we are directly connected to the concept of cost. So this idea that since we are able to accelerate a system, so how we can quantify the cost associated to produce those thermal change. So the idea for in order to quantify this cost, I suggest to go again from the Langevin equation and using the idea of Sekimoto, the idea to develop the first law from the Langevin equation. The idea is to transform a force relation in a relation between energy. And by summing a term in both sides of the equation, the idea is to identify a total differential on this Langevin equation, in which for the first law, the total differential is the change in the internal energy of the system. If you want to apply the same kind of idea for entropic relation, we should divide each energetic term by the instantaneous temperature. And again, by summing a term in which we are able to identify what is total differential for the second law. In this sense, it is the system entropy. So then we are able to identify what is the system entropy by summing this term in both sides of the equation. And doing that, we are able to identify one term that is related to the medium entropy, that's one on the left of this equation. And this middle term corresponds to the generation of entropy. So the idea is that for our step protocol, we need to do a discontinuous change in temperature. There is an instantaneous change on the internal energy of the bath that's given by this variation in temperature. And this instantaneous change is followed by a continuous process in which there is a heat flow between the system and the heat reservoir. If you just look to the internal energy, this heating and cooling process are completely symmetrical. But if you use this idea, this formalism, to looking for the variation in system entropy and the medium entropy, we start to see the asymmetries of this process. This way to define the non-equilibrium system entropy turns to be a function that is discontinuous in the sense that when we produce a discontinuity on the control parameters, when we do an instantaneous change in the control parameter, there is an instantaneous change on the system entropy, in which that is followed that this quantity starts to decay towards the equilibrium condition. So, and using this formalism, it is possible to quantify two different costs for this step change, that is an entropic and energetic cost. The idea that this entropic cost is valid in this case for a discontinuous change, for a single discontinuous change. And by multiplying this entropic cost by the instantaneous temperature, we are able to identify the energetic cost that we call here a dissipative work. So the idea that once we are able to identify the cost, you can go for the next step that is looking for strategies that optimize this transition between two equilibrium states in a given finite time. So the idea for that is to looking for the macroscopic Langevin equation, in which we identify the transition time as a functional of the protocol. In our case, the protocol in temperature. So by looking to this functional approach, we are able to identify two functionals for the cost, one functional for the entropy and the other one for the energetic cost. Here we use this the entropic cost in order to build a functional that's made a trade-off between the transition time in the left and the entropic cost on the right. And those two functionals are related as a trade-off relation by the Lagrange multiplier, in which if we apply a Euler-Lagrange method, we're able to define what is the time dependence of this protocol that minimizes this thermodynamic cost as entropy for a given transition time. And you can quantify here in the sense that if you do a step change in temperature, we have a low cost, but at the same time, we need to wait for a longer time to have stabilization. And you can compare here this thermal easy and the optimal one, both accelerating at the same rate. They are able to make your system to be in an equilibrium state faster, but the optimal strategy decrease the entropic cost. And by this approach, we are able to unveil more asymmetries between heating and cooling process.
Luís, a lot of people are having difficulty. I mean, I've not been able to watch a lot of this. So one suggestion, and it seemed to be a consensus from what I can tell, is if you could set your zoom to the maximum magnification, that might make it a lot easier. And unfortunately, I'm looking at a small screen. And somebody, Artemy is suggesting you hit the key X. Actually, that looks a lot better right there.
Now it's better?
Yeah.
Okay. Yeah, so then this is the last slide, but this idea that with this method, we are able to see constraints, and that these constraints, it's applied in different ways for heating and cooling. Here we see that for cooling, we have a speed limit in which you're not able to accelerate, give below a threshold, and in opposition of heating, that you can accelerate the transition as fast as you can, as long as you produce more entropy. And by this, I conclude that I show an experimental implementation of that provides the possibility to turn the bath temperature as a time-dependent control parameter. And by implementing a time-dependent control parameter as temperature, we are able to implement a shortcut thermalization strategy. And then relate cost functions with temperature increments. And also we relate minimal entropy production by transition time by means of a functional relation. And then we put speed limits and we unveil asymmetries between heating and cooling. With that, I conclude.